In mathematical analysis, we frequently encounter equations defining complex, twisting surfaces, where algebraically isolating a specific variable is strictly impossible. We need a way to prove a solution exists without ever finding the formula for it. To understand the problem, look at an explicit function. This is the math you learn early on. You have an equation where one variable is clearly isolated on one side of the equal sign, delivering a direct output. For example, y equals x squared. Compare that to an implicit function. This equation mixes x and y together. If you try solving for y using standard algebra, you'll immediately hit a wall. You can't factor or divide it away. The variables are tangled. When basic algebra hits a wall, we turn to advanced analysis. We need a tool that looks at the localized geometry of the equation to prove that a solution is hiding in there, even if we can't write it down. The formal derivation for this tool appears in Walter Rudin's Principles of Mathematical Analysis. This text is the rigorous baseline for modern university mathematics. In Chapter 9, Rudin introduces a bridge between basic calculus and high-dimensional spaces, the Implicit Function Theorem. The theorem states that if specific conditions are met, an implicit equation contains a function that exists, is unique, and can be differentiated, all without calculating the formula itself. It maps an unyielding, tangled algebraic equation onto a predictable geometric structure. Here is how Rudin builds the model. This text defines the theorem setup. We are looking at a system of equations mapping a large multidimensional space into a smaller one. Rudin splits the variables into two categories. We have n independent variables, labeled x, and we have m target variables, labeled y, which we want to solve for. Taking the derivative of the system forms a Jacobian matrix of all first-order partial derivatives. We split this matrix into two blocks for the x inputs and y targets. We direct our attention exclusively to the y target block, which is a square. For the theorem to work, this square matrix must be non-singular. Its determinant cannot be zero, meaning it has to be invertible. If this block is invertible, it determines the local behavior of the entire nonlinear system. We can translate that matrix algebra directly into physical geometry to see exactly why a zero determinant completely breaks the system. Look at this winding 2D level curve. Evaluating a single point, we draw a tangent line representing its linear approximation. As we slide to the extreme edge where the curve folds back, the tangent becomes perfectly vertical, the exact moment the Jacobian determinant hits zero. A zero determinant indicates our linear approximation collapsed. A vertical line has an undefined slope, failing the vertical line test required for a valid function. If the geometric surface folds vertically relative to our target axes, it is geometrically impossible to define a clear, single-valued function at that location. If the determinant is non-zero, the theorem makes three promises. First, local existence. Drawing a microscopic boundary around our safe point isolates a tiny curved slice, guaranteeing a valid function. Second, local uniqueness. Inside this box, no extra branches exist. 1x yields 1y. Globally, the full equation might twist and cross itself many times, but locally, inside our neighborhood, the ambiguity is completely eliminated. The third guarantee is differentiability. Because the original implicit equation was smooth, our newly guaranteed local function perfectly inherits those same continuous properties. By checking one algebraic condition, the theorem allows us to surgically extract a predictable slice out of an otherwise chaotic mathematical structure. How does Rudin actually prove these guarantees without writing down the formula for the function? He proves it by bootstrapping an entirely different theorem, the inverse function theorem. The inverse function theorem requires matching input and output dimensions. Rudin constructs a temporary mapping, mapping independent x variables to themselves alongside the y variables. Taking the derivative of this expanded mapping forms a clean identity matrix next to our original target block. This creates a mathematical domino effect. Because the identity matrix is stable, if our target block is invertible, the entire newly expanded massive matrix is also invertible. This invertibility satisfies the strict requirements of the inverse function theorem. Once triggered, it provides the solid proof for the implicit function theorem. The IFT functions as a dimensional mapping used to apply the inverse function theorem to implicit systems. To see how this dictates geometry, let's test the equation of a 3D sphere. X squared plus y squared plus c squared equals 1. To solve for the vertical axis, z, we calculate the partial derivative with respect to z. The result is 2z. Rudin's hypothesis states we can extract a valid local function for z anywhere on this sphere, provided the derivative, 2z, isn't 0. If z is 0, we're exactly on the equator. There, the surface curves vertically, failing the test. But everywhere strictly above the equator, or strictly below it, the derivative is non-zero. The surface is valid, and a local solution is absolutely guaranteed. The algebraic calculation of the derivative maps out the exact geometric boundaries of solvability. This core theorem provides the essential framework required for safely navigating complex high-dimensional spaces in applied mathematics and physics. It is vital in machine learning for optimizing along constraint surfaces. When an algorithm performs gradient descent on a specific algebraic surface, the IFT provides the necessary derivatives to move along that path, even when we lack an explicit formula for the surface. It also allows differential geometers to define smooth manifolds by ensuring that a complex coordinate system can be locally reduced to a simpler functional one. So, to review, these implicit equations can define local functions, and as long as the target Jacobian block is invertible, that localized function is guaranteed to exist, to be unique, and to be differentiable. Even when explicit formulas are impossible to find, mathematics provides a rigorous way to analyze and navigate the structure of the system. If you found this breakdown useful, hit like and subscribe, and join us next time as we continue our journey through the textbook.